Hello everyone. Today we are going to introduce the different form of the remainder of Taylor series. Firstly, I want to briefly introduce the Taylor series. The Taylor series is a form to approximate a function of f by polynomial of degree n near a particular number a. And the Taylor series can be written as the following form, just like this, as we learned in the class. Okay, and due to the Taylor series is an approximation of a function, so we know there must be some difference between the function f of x and the Taylor series. So we can minus the function f of x and the Taylor series, and we can get the difference. And we call the difference as the remainder of the Taylor series. And we know that when the remainder of x is 10 to 0, when the n is 10 to infinity, we can get the conclusion that the Taylor series is equal to the f of x. Okay, and today I want to introduce the two different forms to represent the remainder. The first form is the integration form. The integration form is just like this. And the second form is the Lagrange form. And the Lagrange form is just like this. Okay. Firstly, I want to introduce the integration form. Okay, how can we get the integration form like this? Okay, we fixed x is belong to an interval I, and by the first fundamental theorem, we can get this function, the integration from 0 to x, and the derivative f of t dt is equal to f of x minus f of 0. This is just use the first fundamental theorem of calculus. Okay, and the next, we want to solve this problem in another way. We use the integration by part to solve this function. So we can rewrite it at this form. Because the x minus t's derivative is equal to 1, so we can just rewrite it as this form. Okay, so now we just integration this and the derivative this. Integration this and the derivative this part. So we can use the integration by part to get this function. And we can substitute the t with the x in t in this function. So we get this, and just like this. Okay, and we can use the integration in this part again. So we can get this function. So we repeat this step for many times. So we can get the function below. And this part of this function is just like the Taylor series. And this part plus the f of 0 is just like the Taylor series. And this part is just the remainder of the Taylor series. Okay, and the next, I want to introduce the Lagrange form of the remainder. Lagrange form of the remainder is just like this. And the c is not a constant but a variable in the x and in the 0 and the x. And so we can prove it from the integration form. From the integration form, we can get the r plus 1 of x is just like this form. And by the general mean value theorem of integral. First, we have the brief review of the general mean value theorem of the integral. There exists a function f of x is constant on the interval a, b, and another function g of x is integrable in the interval a, b, and the g of x doesn't change sign on the interval a, b. Then we can get the conclusion that there exists a c is below the ab, such that this formula is true. So we can just see this part is as f of x and this part as g of x. So we can use this formula to solve this problem. So when the x minus t is smaller than 0, we can take the negation out of the integration just in there. So it doesn't matter. So we can just use the mean value theorem of integral, so we can rewrite this formula just like this form. And we can just substitute the x minus t as u, and to do the integration, so we can get this form. So we can learn that the Lagrange form of the remainder is just like this, and the integration form of the remainder is just like this. Okay, this is my introduction. Thank you for listening.